This is joint work with Ajay and Alex Otel, who is somewhere out there. So there's been a lot of talk at the conference about AI as being a general purpose technology for prediction, and we find it as a component in lots of product services and processes. And somewhat sort of following on from the last paper, our focus in this paper is looking at AI as a GPT for discovery. And this is very much following on the discussion over lunch yesterday, and ideas put forward by Ian and Scott Stern and Rebecca Henderson, thinking of AI as an invention of a method of invention, building on that idea of Zvi-Grillakritz. And we also had a similar idea in a previous paper that was published in the NBR conference volume, where we thought of AI as being a general purpose meta technology. And this is following on Paul Romer's idea of a meta idea, which is an idea for producing ideas. Really, what motivates this paper is evidence of very substantial growth in the use of machine learning in the discovery process. And here we just have some examples. I know there's somebody here from DeepMind, but one of the applications that has received most attention is AlphaFold from DeepMind, which essentially has had huge success in predicting protein structures from amino acid sequences. And what's going to be common really to all of these problems is that these are combinatorial type problems, really difficult problems. The protein folding problem is particularly challenging, and DeepMind won the Cas13 protein folding competition by a considerable margin using deep learning techniques. But we see it across a range of areas. So Abe Heifetz talked about the role in small molecule drug discovery, again a combinatorial type problem where you're trying to predict the binding affinities of small molecule drugs with various protein targets, and Abe told us about the success that Atomwise is having. And just a third example is in terms of discovery of new materials, so new materials for energy harvesting and storage, new materials for medical devices. And actually at the one of the lunchtime talks at this conference last year, there was a presentation by Alain Aspero-Guzik, who's been doing some of the pioneering work in the use of AI in materials discovery, and he particularly talked about combining AI with robotics to put in place what he called self-driving discovery processes, or autonomous discovery processes. So this is just a kind of sampling of the way in which AI is being used in the discovery process. And if you think of GDP as a prediction technology as kind of shifting the output production function in a standard endogenous growth model, what we're really interested in here is how it might affect the other production function in an endogenous growth model, the knowledge production function or innovation production function. And the question is, how can we think about this, and how might we integrate that into growth models? So the key ideas in this paper is that we think of innovation as being search over a massive combinatorial search space, something that was common to all those research questions that I had on the previous slide. And the challenge here is that there's huge uncertainty as to the location of successes in that space. Now, discovery is aided by prediction models or maps, and traditionally it would be scientific theory that would provide the models that would allow you to predict where the successes were. And we can think of there being a fitness landscape mapping combinations to the value of those combinations, and to aid that search. You make use of a model of that space. So we also think of discovery as involving a multi-stage process. So a key is prioritizing the combinations that move down that discovery pipeline. And the key conceptual device in this model, and I'm going to have to speed up to make sure I get to it, is the idea of a ranking function, which shows how that prioritization can be made. And the idea then is that AI allows you to produce better maps, essentially shifting that ranking function. So the paper draws a number of literatures. I'm just going to skip by that in the interest of time. But what I want to focus on is a particular two-stage discovery example. So the first stage is prediction, essentially training the prediction model, and then identifying a decision rule for advancing combinations down the pipeline. And there's various ways in which you could come up with this prediction model, and artificial intelligence being one possibility. And then the second stage is testing, and we assume that the test is a determinative test. So the action really in our model is going to be at the prediction stage. So just some notation so that you can follow the little bit of modeling I'm going to show you. A is ideas, or really the things to be combined. An idea can be in a combination or not in a combination, so there can be 2 to the A possible combinations of ideas, a vast space. There is data, which is essentially observations on past successes and failures. And then there is 2 to the A minus D potential new combinations yet to be discovered, given that the D is already, it's either a success or failure. We assume there's some ground truth, a number of successes out there in the space, which we assume that the number of successes is known to the inventor, but the location is not. That's the discovery challenge. And then PR is just the probability of a combination at the OR place in the ranking. What is the probability of success of that particular combination? So I'm just going to focus on this idea of a ranking function. So we can see what the ranking function would look like if you had perfect information as to the location of the successes. So success is a 1, a failure is a 0. And if you knew exactly where the successes were, and you ordered all your different combinations, essentially what you'd have is a unit step function. If we go to the opposite extreme and you have no idea where the successful combinations are, then you just have this flat line. And it's just a kind of random draw. You know there are G successes out there, and so it's just the G divided by 2A minus D is just the probability that a random draw would be a success. So what we're looking for is a function that converges to the unit step function as the fit of the prediction model improves. And we use this logistic decay function, which gives us this nice shape. Now, we just have to have one further constraint on this to make sure that it converges as the value of B goes to infinity in that previous equation, and this is the constraint that we have to put in place. I won't belabor that given the time. And then the basic result of that is as B increases, you will converge to that ground truth. So just in terms of how we link B to the performance of the prediction models, the idea is that the assumption is that there is a monotonic relationship between the fit of the prediction model on a test set and B, so increases in B are associated with improvements in the prediction model. So we recast this in marginal cost, marginal benefit space. So if we just multiply the probability of a success by the value of a success, that gives us the expected marginal value curve, and it'll have the same shape as the logistic decay function. We assume that there's a constant cost of testing equal to C, so the optimum number of combinations to advance down the pipeline is just given by the intersection of the curves. And then we have the key comparative static, essentially, of the paper, so that if you improve the prediction model, in this case we think of the shock as being access to machine learning, that affects the number of combinations that advance down the pipeline, and also increases the total expected value of innovation in this simple example. So we have lots of extensions. I'm not going to go into these. One important extension, however, is that rather than looking for sort of all the valuable combinations, as in the example I just went through, probably a more realistic example when you're looking for a particular combination that has some desired property, but we basically get the same broad conclusion that the improvement in the prediction model is going to increase the expected value of innovation, even though the number of combinations that advance down the pipeline may either rise and fall in that case, depending on the conditions. And we also extend it to a multi-stage process where there's an option to abandon at each stage, so more realistic discovery processes. I know I'm out of time. Next steps in this are really to look at the empirics. The key testable hypothesis here is that increased access to AI should improve discovery. So we're looking at various sources of exogenous variation in access to AI to test that. And there's lots of things I think that you can do also on the modeling side. We really just use supervised learning, but we can kind of bring in reinforcement learning, active learning, contextual bandits, and various types of unsupervised learning and incorporate it into the model as well.